And here's my latest eBay purchase, which goes like so. Hello and welcome back. If you follow the channel, you know that we rescued a scary General Radio Strobotac that had let go of the magic smoke. As its name implies, it's a stroboscopic tachometer made to measure the rotation speed of spinny things. But not any stroboscopic tachometer. The stroboscopic tachometer, the brainchild of MIT professor Harold Edgerton, the father of stroboscopic photography himself. Professor Edgerton is the inventor of many ultra-high-speed photographic techniques, making famous pictures of milk drops, bullets going through an apple, and even the atomic bomb explosion. As someone said in the comments, it escalated quickly. The Strobotac is also a very fun instrument, having magic capabilities for slowing down time, as we demonstrated in the previous episode. My daughter also dubbed it the Mind Reader-nator, as it certainly looks a bit scary. However, I'm not ready to take over the tri-state area with it. All I want to do is to look at the punch cards in our IBM 1402 reader at the Computer History Museum. The cards fly by at 800 cards per minute, so without a good stroboscope you can't see a thing. To watch how repeatable the card position is along the transport, I need to trigger the flash from a card reader signal, or better, from an optical detection of the edge of the card, followed by a flash after a precise controllable delay. And as this was a known application for its stroboscopes, General Radio designed a companion box precisely for that. It's called the Type 1531-P2 flash delay. And wouldn't you know it, I just got one by paying my monthly ransom on eBay. So in this episode we'll try to bring our flash delay back to life and see if we can cobble a homebrew optical pickup head for it. And here's my latest eBay purchase. It's the companion flash delay unit, which goes like so. And you put it in the input, and you're supposed to trigger it with either a photocell or a contact closure, and it will give a delay between the trigger and your flash. And supposedly this is newfangled solid state electronics. Yes! Ooh! There's a little bit of crusty stuff, so some beautiful transistors. And this is more complicated than I expected. And ooh! The electrolytics have had better days. I believe that's just the part supply. Nicely! It's nice construction. It's beautifully done. Okay, so I guess just a recap. Oh, these are bad too. Or at least the sleeves are bad. Not good looking stuff over here. Ooh. Okay. Yuck. Okay. Right here you have a baud resistor or diode. Okay. Recap with much smaller caps. Right, new caps well, new old stock. These are from Gemco, so they might be a few years old already. Okay, and these. Oh, they are other. So I don't know if these are bodge or this one looks like they were put there absolutely on purpose. Yeah, they're from the side. Okay, this guy. Ooh, alright. Okay, 4.7 micro, 50 volts. One, two, three. Okay, caps have been replaced. Alright, this is actually way more involved than I thought. That's the input. You have a 2 transistor amplifier. Then you have a 2 transistor Schmitt trigger. Then you have a 2 transistor flip-flop. So when there is a, I can't remember if it's, I think it's an upgoing pulse, it's going to be amplified, it's going to trigger the Schmitt trigger, and it's going to cause the flip-flop to flip, which is going to cause the unijunction transistor to start charging its RC capacitor here. There's a time delay, after which it will abruptly shut off, which will go either here and make a negative pulse on the output, or go through yet another flip-flop, and that flip-flop is only going to let the first pulse through. So that's for the single flash position, and then in order to reset it, you go here and you ground this. That resets the single flash, arms it again. Or you can use that as a separate input and get switched right here through here. And if you're in multiple position, it will do it by itself. And this is how I wired it up. I'm checking the voltage on the multimeter that you probably can't see. And then I have some pulses going in, and on the output I'm monitoring the pulse out. I have a triggering thingy over here. So I guess I just turn it on and see what happens. Alright, so on. I have 22 volts. Oh, I have my pulses. I think it works already. I see my pulses coming out. So that's my pulse coming in. That's the short pulse coming out. Let me trigger on this better. After a delay. Okay, I have trouble triggering over here. Oh, because I'm in auto. Quick action, there we go. Alright, so I think we are delay. Absolutely, and we have several ranges. Okay, if I put it back over here, I can see our delay move. It's a very short pulse, and then I can move it. Kind of. It's a little jittery at the end. Can I put a bigger delay? Yeah, it's over here now. Yeah. There you go. And can I do an even bigger delay? Yeah, giant delay. Alright, so now how can I test the single that I'm going to go into back into range 1. Over here, I'm going to put it in single. And I'm going to rearm it. Okay, I saw it come once. That works too. Seems to be working plenty fine, thank you very much. Okay. It's fine. After reassembly, then you install it like so, I think, and there you go. Goes to the input. So now if I turn that on, whoops, and wait for a little while, it's tube, okay, now I put it on X, and I turn that one on. There you go, and I should be able to control it externally. I'm controlling it over here. So that's working, it's doing all kind of interesting things with the shutter of the camera. Alright, our Type 1531 flash delay seems to be working plenty fine after a simple replacement of its disgusting capacitors. It delivers a clean delayed pulse after an electrical trigger signal. But for moving things like my flying punch cards, I want to trigger off an optical signal. Genrad made a photoelectric probe specially to work with the delay, but I couldn't find any. So I decided to build my own. Alright, so usually you have some kind of optical pickup that plugs into here. I don't have the original probe, so I made myself one. Eventually what I want to do is have it as a tool on the 1401 that help us debug the card transport in the punch card mechanisms. So I need someone very sensitive with a very large separation between the source and the detector. So I made myself a little circuit. Here's just a transimpedance amplifier and another amplifier with a TL072. Since I didn't have the original optical probe, I needed a quick bit of ghetto engineering to devise my own replacement. I drew up a small circuit in my lab book made of a photodiode and a TL072 op-amp, so I could breadboard it. Here is a quick explanation of the circuit. We start with a pin photodiode from my pile of spare components. Pin diodes work best when reverse biased by a few volts, so I use the convenient -15 volts supply from my breadboard and a trimmer pot for that. Turns out that the adjustment was very insensitive, a few negative volts work fine. When reverse biased, the photodiode produces a tiny current that's directly proportional to its illumination. To amplify that, we need a sensitive current to voltage converter, which goes by the name of a transimpedance amplifier. But it's just a big name for a classic inverting amplifier with its input resistor omitted. It's one of the simplest op-amp circuits you can make. We then put a DC blocking cap on the output. That will get rid of the more or less constant voltage due to the background illumination. In our application, we only want to amplify fast illumination changes when an object goes in front of the photodiode, not the average illumination. The DC blocking cap is followed by a classic inverting op-amp with a gain of about 100. Just guesstimating here, we can adjust the feedback resistor on the breadboard if we need more or less gain. But as you'll soon see, the initial guess was just fine. The output of that goes to the trigger input of our Strobotac delay box with a pot to adjust the amount of signal. That was also very insensitive, but in the middle did it. On the breadboard I also added an infrared LED to illuminate the photodiode. Let's see how that works. And right now it's detecting mostly the 60 Hertz, but if I put a fan in here and get it to spin, it's going to get to find the blade that is contaminated by the 60 Hertz. So probably if I turn that off, yeah, it's better. And then what we want to do is get that guy here, have it shine over here, and turn it on. It's going to have to warm up. While it's warming up, I'm going to turn the lights off. There you go. And now it's getting the pickup, and the blade should look stable. You know, I have to do something on the it wreaks havoc with the camera shutter. There you go. Make it having long exposures, and now it doesn't interfere anymore, and that should be a lot smoother. Yeah, that's a lot more representative of what you see. You can see how I can adjust the delay between the firing of the Strobotac and the pickup, and it allows me to select the angle at which I see the blades. See, varying the delay, I catch the blades later or earlier. Alright, the prototype works a treat, but some of you might have spotted an annoyance. My op-amps need to be powered by plus minus 15 volts, and the circuit needs an analog ground midpoint. Unfortunately, the original probe connector on the Genrad delay box only provides unregulated 25 volt power, which was meant for an illumination lamp. So for the final build, I'll be adding a little voltage regulator and a virtual ground circuit, so I can connect my probe just like the original one using the optical probe jack. We start with an 18 volt regulator powered by the 25 volt lamp power. We then add a simple virtual ground circuit. It consists of a resistor divider that generates a midpoint voltage, which is then buffered by a unity gain op-amp. We tie the virtual ground output to the ground of our previous circuit. Now the upper and lower rails are at plus and minus 9 volts with respect to our virtual ground. We use that to power our unity buffer and all the other op-amps of our probe circuit. We are done with our ghetto probe circuit. For quick one-off projects, I like to use Adafruit's Perma-Proto rather than go through the trouble of designing a PCB. They are little PCBs that mimic a breadboard. I just port the breadboard design over to the Perma-Proto, and voila, we have a final soldered version. And yes, they do fit in Altoid mint candy cans, and I just happen to have one with a transparent window, branded by Regal, no less. Ghetto project complete. Alright, so here's the production version of my little sensor. Now made to work with a single power supply, which means I can pair it with the sensor supply that was originally meant for the original sensor. There you go. And here's the little LED. Goes in there. Goes underneath. And now we turn this on. We turn that on. We turn the lights off. We wait a while. And here we have it. And of course, if I don't use the box, right, if I go back here and don't use the synchronization box, it's still working, but it's not synced, right? I can probably get it slow. Alright. whether if I sync it. There you go. Now it's going to be stable, and the delay is going to be controlled by here. Alright, that's all we really wanted to achieve with this update on our Strobotac. See you in the next episode!